In Lab 13, we're going to be looking at the structure of covalent compounds. We're going to be counting the number of valence electrons in order to draw the Lewis dot diagram, and then we will take the diagram and figure out what the geometry of the molecule is. So let's look at how to draw the Lewis dot structures of these covalent compounds. So I usually start off by counting the total valence electrons next. I know that's labeled as number 2, but I usually like to count them first just to see how many valence electrons I have. Once I have the valence electrons, then I'm going to sketch the skeletal structure using the element symbols. So how you do that is, in this lab you're going to be given the compound name. From that name, you're going to figure out what the chemical formula looks like, because the chemical formula is going to consist of the element symbols and how many of each of those atoms are present. You're going to start drawing the skeletal structure by putting the least electronegative atom in the center. Now, 90% of the time, this is going to be the first symbol or the first atom in the chemical formula. Not always, but most of the time. Hydrogen is going to be in the terminal position, meaning it will not be the central atom. We will see in this lab halogens sometimes being terminal and sometimes being the central. Now you have your general structure, you have your total valence electrons counted. So a refresher on how to count the total valence electrons. You're going to be looking up each element present in the chemical formula, how many there are of each, and then adding the total. And we'll show an example of this when I work through one of the problems here in a minute. What I want to point out now is that if you have a polyatomic ion of any sort, so when I say a polyatomic ion, what I'm talking about is if you have covalently bound atoms with a charge. Okay, so whether it's a cation or an anion, you need to take that into account when you're counting your total valence electrons. If it's a cation, so if it has a positive charge, you're going to subtract that number of electrons. If it's a polyatomic anion, so if it has a negative charge overall, you are going to add electrons. So an example would be the sulfate ion. So notice it's got sulfur and oxygen. Those sulfur and oxygens are covalently bound. Now, the first element present, S, sulfur, that's going to be my central atom. It's also the least electronegative. So if I'm drawing the skeletal structure of this, I'm going to put S in the middle, and then I'm going to take these 4 oxygens and put them around that sulfur. Now when I'm counting the valence electrons, I want to take into account that there's 1 sulfur and 4 oxygens, but I also want to take into account this charge. So since it's a negative charge, I'm going to add that number of electrons. In this case, a -2, so I'm adding 2 extra electrons to my overall valence electron count. So in this case, I have sulfur, oxygen. So how many atoms of sulfur do I have? Just 1. How many atoms of oxygen? 4. Then I'm going to take the number of each and multiply it by the valence electrons that they contribute. Now sulfur is in group 16, so it's going to contribute 6 valence electrons. Oxygen is the same, it's in the same group as sulfur, so it's also going to contribute 6. So that means I have 6 electrons coming from the sulfur. 4 times 6, I have 24 electrons coming from the oxygens. So to figure out my total valence electrons, I want to add those together, but I also want to add in those 2 extra electrons from that charge. So my total is going to be 32 valence electrons for that molecule. Okay, let's move on and see what's next. So as you saw in the previous slide, here in step 3, it says to connect the central atom to the surrounding atoms with a single bond. So that's where we had the sulfur with a line and then the oxygen. This line is representing a single bond, and it is worth 2 electrons. Because what's actually happening is, since it's a covalent compound, we have the sulfur with an electron and the oxygen with an electron. They're both sharing those to make a single bond, 2 electrons. Next, we want to place the electrons as lone pairs around the terminal atoms first. So the goal is to make the terminal atoms happy first. How do you make them happy? By giving them 8 electrons. That's the octet rule. Most atoms want 8 electrons to be happy. Of course, there's exceptions to every rule, one of those exceptions being hydrogen that only needs 2 electrons. So in the case of that sulfate ion, we had sulfur with 4 oxygens around it. If you remember from the previous slide, we had 32 total valence electrons. So to make the terminal atoms happy first, what I'm doing is I'm adding 6 more. Because this single bond here, going between the sulfur and the oxygen, that's worth 2 electrons. So this oxygen wants 8, that's what the octet rule is saying. So to give it 8, I'm adding 6 more electrons to it. So that oxygen's now happy, it has a total of 8. I'm going to do the same thing to the other 3 oxygens, adding 6 electrons to each of them to give each of them a total of 8. So I've completed step 4. Now step 5 says subtract the electrons used so far from the total number. Okay, so let's count and see how many we've used. Remember, we had a total of 32 to start with. So I'm going to write 32 and I'm going to subtract how many we've used so far. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've used all 32. So that means I have no more electrons to add. Step 6 says if the central atom lacks an octet, you can move one or more lone pairs from an outer atom to make a double or triple bond. So sulfur, it has 4 single bonds around it. Each single bond represents 2 electrons, so this sulfur does have 8. Okay, so to write this, since it has a charge, remember it had a 2- charge, you want to make sure to put brackets around it and then this 2- on the outside. That's just telling the person that's looking at this Lewis dot structure that there are 2 extra electrons on there because of that 2- charge. So this is one way to draw the sulfate ion. We're going to talk about some exceptions which will bring about a new way to draw this Lewis dot structure. And the exceptions to the octet rule. Now, this is going to help you answer questions for the pre-lab for lab 13. So there are 3 different exceptions to the octet rule when we are drawing Lewis structures. One is an incomplete octet. So what that means is sometimes you have elements that don't need 8 electrons to be happy. Okay, and we talked about hydrogen being one of those elements. Hydrogen just wanted 2. That's all it can hold. It can't hold anymore. Well, another exception is boron. And an example would be this boron trihydride compound. Now, when I'm drawing this Lewis structure, say I wanted to count my valence electrons first. Well, I have boron and I have hydrogen. We look at how many atoms of each. So I have 1 boron, and then this subscript of 3 tells me I have 3 hydrogens. Next, I look up their number of valence electrons. Well, since boron is in group 13, it has 3 valence electrons to contribute. Since hydrogen's in group 1, it has just 1. So I'm going to multiply across. I get 3 plus 3. There is no charge on the molecule, so that's it, just those 6. So I have 6 total valence electrons when I'm drawing this structure. So next what I want to do is I want to draw the structure connecting with single bonds only to start. So I have boron with 3 hydrogens around it. I'm going to connect those 3 hydrogens with single bonds. Okay, my next step is to make the terminal atoms happy first. Well, we said hydrogen only wants 2 electrons, and this single bond here represents 2 electrons. So the hydrogens are happy with just that single bond. So I don't need to add anything else to them. So no extra electrons added to them. They're happy. Okay, well the next goal is to make this central atom happy. In this case, boron. But if I look, I've used 2, 4, 6 electrons. I've used all 6 that I have available to me with those 3 single bonds. Now that means boron only has 6 electrons around him. And we said that everybody wants 8. Well, not boron. Boron is happy with just 6, so he is one of the exceptions to the octet rule. 6 electrons, and he does not need 8. So this is the correct Lewis structure for the boron trihydride molecule. Another exception to the octet rule is now an expanded octet. So notice for the first exception we said incomplete, meaning less than 8. Well, so expanded then means more than 8 electrons. And we can see this only for elements in period 3+. And that's because elements in period 3+ have d orbitals. They have extra space to put extra electrons in. One of those examples would be phosphorus pentachloride. So for phosphorus pentachloride, we have phosphorus being the central atom, and then we have 5 chlorines around it. Okay, and I'm not going to count out the valence electrons on this one. I just want to show you that it has more than 8 electrons. So we have phosphorus with the 5 chlorines around it. So now looking at this, I mean, the goal is to make the terminal atoms happy first, but what I want to focus on is phosphorus here. So notice phosphorus has 5 single bonds around it. 1, 2, 3, 4, 5. Remember, every single bond counts as 2 electrons. So if we have 5 single bonds, each with 2 electrons, phosphorus has 10 electrons around him. That's more than 8, but that's fine. He can have an expanded octet because he's in period 3 or higher. So we might see that happen sometimes as well. Now the third category. These are molecules with an odd number of valence electrons. These are often referred to as radicals. Now they are very, very reactive because what happens when you have an odd number of valence electrons is you can't have electron pairs anymore. And if you don't have electron pairs, you come up with a very unstable molecule. And an example of this would be this superoxide. So we have O2 with a -1 charge. So let's work through this and see how it would look. So we have 2 oxygen atoms. Let's start with our valence electron count. So we have oxygen, 2 of them. Since they're in group 16, they have 6 valence electrons to contribute to the cause. That gives us a total of 12. But remember, if there's a charge, we have to take that into account too. And in this case, it's a -1, so we're going to add 1 more for a total of 13 valence electrons. So now that I know I have an odd number of valence electrons, that tells me there's a radical, that I'm going to have an unpaired electron. So when I draw this structure for the Lewis structure, since there's only 2 oxygen atoms, I'm just going to connect those 2 with a single bond, so there's no central atom in this case. Now my goal is to make everyone happy, right? And I have 13 electrons to do that with. So far I've used 2, so I'm just going to pick an oxygen atom and try to make him happy. So to do that, I'm going to start with this guy. I'm going to add 6 more. So now this oxygen here has 2, 4, 6, 8. So he's happy. I've used 8. Well, if I've used 8, how many do I have left? I just have 5 left, right? So if I have 5 left, that means I can't add 6 around this other oxygen because I don't have 6 to give. I can only add 5. So look what happens there. If I can only add 5, I have this lone electron right here that's not paired up with anything else. That lone electron is making it a radical. It's making it unstable. Okay, because this Lewis structure has an overall of a -1 charge. So once we have the Lewis structure, then what do we do? Well, the next step is to come up with the electron pair geometry or the molecular geometry. And to do this, we're using Vesper theory. And what Vesper theory is it's the valence shell electron pair repulsion. Vesper theory helps us predict the 3D shape of molecules, so what they look like in 3D based on the repulsions of the electron pairs. So the lone pairs on the atom, on the central atom, are going to help determine the shape. So there are 6 steps when trying to figure out the shape based off of the Lewis structure. Well, first off, you need the Lewis structure, so that's why it's the first step in this lab. Next, you count the things around the central atom. So when I say things, that means each atom counts as a thing. Doesn't matter if it's bonded with a single, double, or triple bond, it's just one thing. Electron pairs also count as a thing. You want to next draw the basic shape using the element symbols and make sure to indicate if it's a single bond, double bond, or triple bond using 1, 2, or 3 lines. You always want to take into account lone pairs and then adjust angles accordingly. So let's start with the first category. If there are 2 things, it's going to be linear. So what do I mean by things? That's how many atoms or how many lone pairs are on the central atom. So an example would be carbon dioxide. Notice carbon is the central atom. It is bonded to 2 oxygens, both with double bonds. Now, if I'm counting the things around the central atom, carbon, I just have 2 atoms around carbon. 1 oxygen here, 1 oxygen there. So that's a total of 2 things. The fact that there's double bonds does not matter. I'm also not taking into account the lone pairs on the oxygen. I'm just focusing on the carbon itself. Whenever you have 2 things around the central atom, the shape is going to be linear, and the angle, therefore, is going to be 180 degrees. And we're talking about the angle from one oxygen all the way to the other. All binary compounds are linear. That means is if there's only 2 elements involved, it's going to be a linear compound. You don't have a central atom with a binary compound, but it's still linear. We'll see some examples of this in class as well as in lab. So on the handout supplied to you, that would be this category that we're looking at right now. So the first number is the number of things, and we said there were 2 things, 2 atoms more specifically. The second number, where we see a 0, that's how many of those things are lone pairs. So what we saw in the previous example, that there were 2 things around carbon, but both those things were atoms. So that means 0 of those things were lone pairs. So we follow this category over and see how to draw the shape. Of course, we would insert the symbols. We would put a C here, an O here, and an O here, not just dots. But we follow along and it tells us the name, linear, and it also gives us the angle. So we'll be using this chart to classify several different Lewis structures to figure out their shape. Next, let's look at what if there are 3 things. So for 3 things, trigonal planar is the basic geometry, but there are variations. So looking at 3 things, we have 2 shapes that it could possibly be. So if it's trigonal planar, if that's the shape, that means that the 3 things around it are all atoms. So the example I have here is boron with 3 fluorines around it.
Notice boron has 3 atoms, but 0 lone pairs on it. So we're just looking at the central atom itself. When you have a trigonal planar shape, the bond angle is going to be 120. Okay, now imagine taking that shape and removing one of the fluorines. Okay, so if I removed an atom and replaced it with a lone pair, what we're going to get is a bent geometry as shown in this sulfur dioxide example. So here we have sulfur. It has 3 total things around it, oxygen atom being one thing, the other oxygen atom being another thing, and the third thing is a lone pair on the sulfur itself. So it has 3 total things, but 2 of those things are atoms and 1 is a lone pair. So due to 1 being a lone pair, that changes the shape. We now have a bent molecule, and the bond angle is going to be less than 120 now. Whenever you replace an atom with a lone pair, you have larger repulsive effects. So this is why the angle is decreasing. It's going to be less than 120 instead of 120, which the trigonal planar example had. So how do we find these shapes on the handout? Well, the first example, the boron trifluoride molecule, had 3 things around it, 3 atoms, 3 fluorines, and 0 lone pairs on the central atom. So that tells us that it's trigonal planar and the bond angle is 120. In the example of sulfur dioxide, there were 3 things around sulfur dioxide, 2 atoms and 1 lone pair. So the second number represented asks how many of those things were lone pairs, and our answer is 1. It had 1 lone pair. So we followed this category. It shows us the shape, tells us the geometry is bent, and that the angle is less than 120. So we are adjusting the angles using a less than or more than sign. So generally when we replace an atom with a lone pair, it's going to be less than. Lone pairs and multiple bonds need more space. That's why the angles are less, not more. Now let's look at 4 things. So the 4 things category, notice there's several different shapes it could be. So you really need to pay attention to how many of those things are atoms and how many of those things are lone pairs. So let's look at the first geometry. The first geometry is called tetrahedral. So this is the case where the central atom has 4 things around it and all of those things are atoms, so 0 lone pairs. In this case, the bond angle is 109.5. We'll notice the shape itself too. We're starting to draw in 3D. So the 2 hydrogens with the straight lines, the reason they have straight lines is because we're saying those hydrogens are in the same plane as the paper. This hydrogen down here is coming out of the plane of the paper. I know that because of this wedge. So you draw a wedge and then the atom to indicate that that hydrogen is coming out of the plane of the paper. A dashed line, therefore, represents the hydrogens going into the plane of the paper. We're doing a lab where we're going to be building some of these molecules with molecular models. And so you'll actually see what this looks like in 3D rather than just on a slide or a piece of paper. It is important to include dashes and wedges when needed. So now let's look at the second one. So if we took one of those hydrogens, if we took one of those atoms and replaced it with a lone pair, what we would get would be a trigonal pyramidal shape. So now we have nitrogen as the central atom. It has 3 atoms around it and 1 lone pair. So that lone pair is going to take up more space than a single bond. So notice our bond angle is going down, so it's going to be less than 109.5. This element, or compound I should say, in particular, its bond angle is 107. You don't need to memorize that angle, just know that it's going to be less than 109.5. The last shape is going to be bent. So in a bent shape, now we have taken 2 of the atoms and replaced them with lone pairs. So in this example, we have water. Water is going to have 2 hydrogen atoms around it and 2 lone pairs. So it still has 4 total things. It's just 2 of those things are lone pairs. This is going to make the bond angle even less than 109.5. So all of these categories are listed here. The first one, 4 atoms, 0 lone pairs, tetrahedral. Then in that next example, nitrogen trihydride, where there were 4 things, but one of those things was a lone pair. And then last but not least, 4 things, 2 of them a lone pair. That was the water example, and it was a bent shape. So you can use this handout to help you figure out the shape, how to draw it with the dashes and wedges, figure out the geometry itself, and also the angles. Now let's look at when there are 5 things around the central atom. So in the case of those 5 things being all atoms, the shape you would get would be trigonal bipyramidal. In this case, we have a phosphorus atom with 5 chlorine atoms around it. Notice there are 0 lone pairs on that phosphorus atom. You have 2 different bond angles, 90 and 120. So imagine taking one of those chlorine atoms, removing it, and replacing that with a lone pair. When that happens, the shape you will get is a seesaw shape. So you can see in the picture below that this looks kind of like a seesaw, like you would see at a park. These 2 F's being the base, and then the straight line across being the places where you sit. This is going to make the bond angles now be less than, because remember, lone pairs take up more space than an atom and a single bond does, so it's going to be making those angles less, pushing down on those fluorines more. So taking yet another atom away and replacing it with a lone pairs get us the T shape. So this would be 5 total things around the chlorine in this case. 3 of those things are atoms. 2 of those things, are lone pairs. And you'll notice when we draw the actual shape of these molecules, we don't include the lone pairs in the shape. So if you take away the lone pairs, you get the shape of a T, hence the name T-shaped. Next, we have linear. This is where there are just 2 atoms around the central atom and 3 lone pairs for a total of 5 things. So you have a linear molecule from the fluorine to the xenon to the other fluorine.
The last category we're going to look at are when there are 6 things around the central atom. So the basic structure for this would be the octahedral shape. The octahedral shape is formed when the 6 things that are around the central atom are all atoms, so no lone pairs on the central atom. This makes the bond angles 90 degrees all around. So you'll notice in the case of 6 things that we have an exception to the octet rule for all of these structures, and that exception is an expanded octet. They have more than 8 electrons around the central atom. Now imagine taking away one of these atoms, one of these fluorine atoms, and instead replacing it now with a lone pair. So when we do that, what we get is a square pyramidal shape. So now we have just 5 atoms around the central atom and 1 lone pair. So it's still a total of 6 things, it's just 5 of them are atoms and 1 of them is a lone pair. Now doing that again, so removing another atom and replacing it with a lone pair. So now we have square planar. So in this first structure, this would be the electron pair geometry where we are showing the electron pairs as part of the geometry. The next structure, you can see the shape a little bit better because we're not describing the electron pairs as part of the geometry. So it's just a square planar molecule. All angles 90 degrees.
So why do we want to know the shape of a molecule? How does it help us to know that a certain molecule is trigonoplanar versus trigonopyramidal? Well, this is going to help us figure out its polarity. So far we've figured out use electronegativity values to determine whether a covalent bond is polar or nonpolar. But what we were looking at is just the bond itself, not the molecule as a whole. So we figured out that one specific bond based off the electronegativity values. So we subtracted them and then used this chart here to figure out if it was nonpolar or polar, which range did it fit in. Well, now what we're going to do with the structures, the geometry, we're going to use it to determine whether the entire molecule is polar or nonpolar. Because you can actually have polar bonds on a molecule where individual bonds are polar, yet the molecule itself is nonpolar. So the geometry is going to help us figure that out. So one way to figure this out is by calculating the net dipole. So what a dipole is, it's a separation of charges between two covalently bonded atoms. We represent it by vectors, and the vectors that I'm speaking of are the arrows in the picture below. So usually what we have is the arrow points towards the more electronegative atom. So in this case of carbon dioxide molecule that we have below, oxygen is the more electronegative atom, so we would draw a vector pointing, or an arrow pointing toward the oxygen. Well, that's just one of the bonds. There's another bond going from carbon to another oxygen. So we would then draw another vector pointing towards the oxygen because oxygen is more electronegative than carbon. So in the case of this carbon dioxide molecule, what happens is those vectors cancel each other out because we have one going to the right and one of equal magnitude going to the left, making them cancel. So when the vectors cancel, we get no net dipole, 0. Okay? So if we have no net dipole, that means the molecule itself is nonpolar. So even if that carbon-oxygen bond is polar, the molecule as a whole, since the arrows cancel, is nonpolar. So let's look at when the arrows don't cancel. So in the example of water. So water, H2O, is a polar compound. So how do we figure that out? Well, we can figure it out one way by using this net dipole method. So between hydrogen and oxygen, so looking at just one of those bonds, oxygen is more electronegative than hydrogen. So once again, I'm drawing an arrow pointing towards the oxygen. Well, I need to do it to all bonds present, so I do it again to the other hydrogen-oxygen bond. So now, notice since this molecule is bent, because when we draw the Lewis structure, we go through all the steps to figure out the shape, we'll see that that oxygen atom actually has 2 lone pairs on it. So that oxygen will have a total of 4 things around it, 2 of those things atoms, 2 of those things lone pairs, giving it a bent shape. So since it has a bent shape, now the vectors don't cancel each other out. So imagine picking up these arrows and adding them from head to tail. So I'm going to take this first arrow that goes in this direction. Okay, so that's this arrow here. Then I'm going to pick up the other arrow and add it to this one. And you always add arrows or vectors head to tail. So that arrow is going in this direction. So notice they're not canceling each other out. We have a total net dipole from the very tail of the arrows to the head of the arrows. So if we have a dipole, if the arrows don't cancel each other out, that tells us it is a polar molecule. Another way to figure out if the molecules are polar or nonpolar is by applying the rules on the following slides. So for this first slide, we're talking about nonpolar molecules. So you can actually apply these rules to the Lewis structure. You don't even have to know the molecular shape of it. So the first rule says molecules that have no lone pair on the central atom and all terminal atoms are the same, it's going to be nonpolar. So there's 2 examples shown here. So I have carbon tetrachloride, so carbon with 4 chlorines around it. So it is a molecule and it has no lone pairs on the central atom, no lone pairs on the carbon. And all the terminal atoms, so all the atoms that's attached to it, are the same. They're all chlorines. So that means this is nonpolar. I don't even have to draw my vectors. Just with those rules, I can tell you it's nonpolar. However, if you have a central atom with no lone pairs, but the terminal atoms are not the same, so if I replace one of these chlorines with a hydrogen now, looking over here, I've now changed the game. It's now going to be polar. So you need to make sure it fits both. No lone pairs on the central atom and all terminal atoms the same. Let's look at the next rule. So molecules that are made up of only carbon and hydrogen are always going to be nonpolar. So what that means is if you only have carbon and hydrogen present, no other elements, so if you throw in an oxygen or a nitrogen or anything else, this doesn't apply anymore. But if it's just hydrogen and carbon, it's going to be a nonpolar molecule. It doesn't matter if you have 52 carbons and 87 hydrogens, it's still going to be nonpolar. This is very helpful because a lot of hydrocarbons, that's what compounds with carbon and hydrogen only are called, hydrocarbons. With hydrocarbons, they often get to be very, very long chains. So you can have extremely large molecules. And in that case, it's going to be really hard to try to draw the shape, figure out all the vectors. So this one's very useful. Saves you a lot of time. Last but not least, diatomic molecules with two atoms of the same element. So if you have a hydrogen and hydrogen attached to each other, their electronegativities cancel each other out, so it's going to be nonpolar. Same goes with any of the other diatomics. There are actually 7 elements on the periodic table that exist as diatomics in nature. Hydrogen, oxygen, chlorine, nitrogen, and the rest of the halogens as well. So now let's look at some rules we can apply to figure out if a molecule is polar. So molecules that have one lone pair on the central atom, or when all terminal atoms are not the same. So we've looked at this second example already. Okay, this was the no lone pair example. When we replaced the chlorine with a hydrogen, we said, okay, now it's polar. But the first part of this rule says if there's a lone pair. So no matter what, if you see a lone pair on a central atom, it's going to be polar. So you don't even have to know the shape yet. You can just have the Lewis structure and see, hey, there's a lone pair, it's polar. The next rule says molecules with more than one lone pair on the central atom are usually polar. So most of the time, 90% of the time, but there are some exceptions. Water is not an exception. Water is a polar molecule. You can see in the example, there are 2 lone pairs on that central atom of oxygen, making it polar. And you couldn't see it, so going back over to this nitrogen trihydride example, it might be hard to see, but there is a lone pair on the nitrogen. So that's why nitrogen is polar. There's a lone pair on the central atom, causing it to be a trigonal pyramid. Couldn't think of the name. All right.
Let's look at an example of the nitrite ion. So this is one of the compounds in the lab that you need to solve for. And what you need to do is start off by coming up with a chemical formula. So you can look at your polyatomic tables to find this, or look it up on the internet, wherever helps you best. So the nitrite ion, it's ITE, so the chemical formula is NO2, and it has a -1 charge. Now, that's the chemical formula, so we've solved part of this first one. Next, it wants us to calculate the number of valence electrons. And remember, to do that, it's easiest to make a list of the elements present, so nitrogen and oxygen, write how many of each. So we have 1 nitrogen and 2 oxygens. I know that from the chemical formula. And then look up their valence electrons according to where these elements are on the periodic table. So nitrogen's in group 15, so it has 5. Oxygen's in group 16, so it has 6. So this gives me 5 coming from the nitrogen, 12 coming from the oxygen, but I can't forget this -1 charge, Okay, since it's a negative, that means there's an extra electron, so I want to add one more electron to this total. So that's going to give me a total of 18 valence electrons to play with when I'm drawing the Lewis structure. Now for the Lewis structure, you want to start by putting the central atom in the middle and then the other atoms surrounding it. So I have nitrogen, and I'm going to put an oxygen on either side. The goal then is to make the terminal atoms happy first, and the terminal atoms in this case are the oxygens. So what I'm going to do is I am going to make sure each oxygen has 8 valence electrons. So 1, 2, 3, 4, 5, 6. So I've added 6 to it because that single bond counts as 2 more for a total of 8. I'm going to do the same thing to this other oxygen. So now the terminal atoms are happy. Before I make the central atom happy, I want to count and see how many electrons I've used. So I've used 2, 4, 6, 8, 10, 12, 14, 16. So I've used 16 valence electrons. So what that means is, if I use 16, I have 2 left. So what I'm going to do is I'm going to take those 2 valence electrons and I'm going to put them as a lone pair on the nitrogen. Because notice the nitrogen just has 2 single bonds. So that means it only had 4 valence electrons before I added that electron pair. Well, now the nitrogen has 6. 2 from one single bond, 2 from the other single bond, and then 2 from that electron pair. But nitrogen wants 8. So the next step then, if you've used all your electrons, which we have, and the central atom is not happy, what you can do is you can take a lone pair from one of the terminal atoms. So I'm going to take this lone pair here, these 2 electrons, and I'm going to make a double bond. So that's going to change my structure so that now I have nitrogen, double bond, oxygen. And since I used one of those lone pairs, I only have 2 left remaining. 2 lone pairs on this one remaining. The other oxygen still has the 6 total electrons. Since it has a -1 charge, I'm going to put brackets around this Lewis dot diagram and a negative charge on the outside. So this bottom version here, whoops, forgot my electron pair on my nitrogen. So this would be the correct Lewis dot structure. Everybody's happy, I've used all 18, and since it was an ion, I put a negative charge on the outside of the brackets. Okay, next, how do you do the electron pair geometry? Okay, so for the electron pair geometry, we need to figure out the geometry. So to figure out the geometry, we need to count how many total things are around the central atom. So we're looking at just the central atom. So this oxygen atom, that counts as 1 thing. This other oxygen atom counts as 2 things. It doesn't matter that one has a single bond and one has a double. We're just looking at the total things. So this oxygen 1, next oxygen 2. Now notice there's also a lone pair on the central atom. Lone pairs also count as a thing, so that's going to be my 3rd thing. So when I'm trying to figure out the shape, I need to look in the 3 category. So I have 3, 0, 3, 1, 3, 2. Now this first number is the total things. And I have 3 total things, so it could be any one of these. What comes after the comma is how many of those things are lone pairs. Well, if I look at my diagram, nitrogen only has 1 lone pair on it. So I'm looking at the 3, 1. So this diagram here, this shows the molecular geometry. It tells me that it's bent and that the angle is less than 120. So what this is answering is the molecular geometry, so that's here. So I'm going to put nitrogen, and I'm going to draw it so that it looks like it's bent. So I'm not going to draw it linear how it's drawn in the Lewis dot diagram. So this would be my molecular geometry. My bond angle is less than 120. So what's the difference between the molecular geometry and the electron pair geometry? Well, the only difference is you're going to draw it bent again, but this time you're going to draw a line and then the lone pair. So that's the only difference. So let's go to the last piece. Polar ionic or covalent, excuse me. So you want to look at the molecule and answer all of these questions. So first off, I'm going to start at the bottom and work my way up because the covalent and ionic, those are the easier ones to figure out. I'm going to check yes for covalent because there are covalent bonds present. The bond between nitrogen and oxygen is a covalent bond. But I'm also going to click ionic. So why am I saying yes to ionic? Because it's a polyatomic. It has an overall charge. It's an ion. Okay, so if there is no charge on it, you wouldn't click that box. You would click the no for ionic. And we'll see an example of that next. Now the last is it polar or is it nonpolar? So this is where you can use, on the previous slides, you can either do the dipole moment, if that way makes more sense to you, where you're figuring out which one's more electronegative and seeing if the arrows or the dipole moments cancel out. Or you can use the rules that we looked at. And one of those rules said, if there's a lone pair on the central atom, it's going to be a polar molecule. So I'm going to click yes to polar because there's a lone pair on the central atom. And if you do the dipole moments, you'll see that they don't cancel. So for the nonpolar, I will select no. So that's how you complete this chart. Next, we're going to look at phosphorus triiodide. So I wanted to show an example of a compound that was not an ion. So we're going to go through the same steps. So for phosphorus triiodide, the chemical formula would be 1 phosphorus and then 3 iodines. Next, we want to count the number of valence electrons. So we have phosphorus and then iodine. We have 1 phosphorus atom and 3 iodine atoms. Looking at the periodic table, phosphorus is in group 15. So it's going to donate 5 electrons to the cause. Iodine's a halogen in group 17, so it's going to donate 7 electrons to the cause. So we have 5 plus 21 to give a total of 26. So that's how many valence electrons I have to play with. So next is to draw the Lewis dot diagram. So I'm going to put phosphorus as the central atom, and I'm going to put the iodine atoms around it. Once I have the basic structure, I want to make the terminal atoms happy first. So let me switch to yellow here, and I'm going to add 6 electrons to each of these iodine atoms to make a total of 8 with the single bond that they have. All right, so now my terminal atoms are happy, and I want to make my central atom happy. But first, let's see how many electrons we've used. So 2, 4, 6, 8. 8 times 3, I've used 24. So if I subtract the 24 I've used from the 26 I have to use, I have 2 left. So those 2 that I have left, I'm going to put on the central atom. So now, notice phosphorus has 8 electrons now as well. So everybody's happy, and this would be the correct Lewis dot diagram for phosphorus triiodide. So in order to figure out the molecular geometry and the bond angles, we need to look up in our tables. So in this case, we have 4 total things around the central atom. So 1, 2, 3, and then the 4th thing is this lone pair right here. So I want to look in the categories of 4s. So I have 4, 0, 4, 1, 4, 2, and 4, 3. So 4 total things. What comes after the comma is how many of those things are lone pairs. So in this case, we have just one lone pair, so we're going to be looking at 4, 1. So this is how I want to draw the shape in the molecular geometry category. And then I also have the bond angle. So remember, the bond angle is this last column here. It's telling us that it's going to be less than 109.5 because we've added that lone pair, making the bond angle less. The shape itself, I have phosphorus in the middle. And then I have an iodine. The wedge, remember, means that it's coming out of the plane of the paper. So like at you. And then the dashed line means it's hiding behind. So that's the molecular geometry. No charge on it. For the electron pair geometry, it's going to be very similar, except for you're adding a line up here with the electron pairs on it. Hopefully your drawing skills are better because you won't be using a mouse to try to draw these structures. Okay. Oops. So we've answered or filled in all the blanks. The last thing we have to do is check the boxes. So first and foremost, is it covalent? Why, yes it is. Is it ionic? No, no charges involved. Right? It's not a polyatomic ion. Now for the polar or nonpolar, okay, so you can do your dipole moments, which is pretty hard once you get to these 3D structures, or you can use the rules that we looked at before. And the rule said if there's a lone pair on the central atom, which there is, then it's going to be polar. So I'm going to go ahead and click yes for polar, which means that no, it is not nonpolar.